that works perfectly well anytime chi of -1 is -1. We never really need this hypothesis. So one formula when chi of -1 is equal to -1, those are called odd characters, and we're going to see that we're going to have to distinguish these when we prove the functional equation too. In that case, we just get that L of chi 1 is G of chi over L, because, sorry, this minus sign cancels this minus sign, and then we get the sum when B is equal to 1 to L, chi inverse of B, and then we worked out what the argument was and how things canceled, and it just turned out to be the rational number B over L. Well, it was B over L minus a half, but again, since chi is a non-trivial character, when you sum over the values of this times a half, you get 0, right? So this was the formula that we had, and then we specialized it to the case where chi was chi inverse, where we could calculate the Gauss sum, and we could calculate, all right. Now, what does the formula look like in the other hand? So that's the odd case. What about the formula when chi of -1 is equal to +1? Those are called the even characters. But here we have to remember that we're taking chi not equal to 1. So we have L minus 1 over 2 odd characters, but we have L minus 3 over 2 even characters, which are not 1, because it's half of the characters, and then we have to take away the trivial character. Okay? All right, now in this case, we can ignore the imaginary part of this logarithm, because the arg of 1 minus the zeta to the b is equal to minus the arg of 1 minus zeta to the minus b. They're complex conjugate numbers, right? And so in one of these, we have a plus sign for chi. In the other one, we have a plus sign. Whatever the value of chi is on b, you have the same value on minus b, and these things cancel out. And so there we only get the real part. So you get a completely different looking formula. It's minus g of chi over L, because in this case, chi of -1 is +1. And then we have the sum of chi inverse of b, the log of the absolute value of 1 minus zeta to the b, where b is equal to 1. Good? Okay. So this is obviously a much more complicated. These are just rational numbers. These are logs of absolute values of numbers. But we're going to take a little look at that a little bit more closely. For example, what does it say in this case when chi squared is equal to 1? Well, chi squared is equal to 1. That gives the character, and if it's even, that means we saw there was a unique quadratic field contained in Q mu L, where this is the squares, the subgroup of index 2, and in the case where the quadratic character is even, that quadratic field is the square root of L. So this is L congruent to 1 mod 4. In that case, L was 3 mod 4. What does it say in that case? Well, see that because the character here is chi of A is just A over L. So that's even precisely when L is 1 mod 4. Okay, so what does that say in this case? Well, if you think of this is just a plus or minus 1. So and we know g of chi in that case is the square root of L. So we get that L of chi 1 is minus 1 over the square root of L times, I'll just write it like this, the log of the absolute value of the product over the quadratic residues of 1 minus zeta to the A divided by the product over the non-residues of 1 minus zeta to the B. Take the absolute value of all that, because if you take the log of this absolute value of the product, you get plus signs for the logs here, and you get minus signs for the logs there. Good? Okay. And chi and chi inverse are the same thing. Just depends on whether you get a plus sign for the quadratic residues and you get a minus sign for the non-residues. Okay, maybe I should have called this B so it looks the same as before. So So let's analyze that formula a little bit. So I have to talk a little bit about what 1 minus zeta is and why that's a formula very close to our original class number formula. So consider the element u, well, maybe I better call it something else, y, which is zeta minus 1, an algebraic integer in the field of L roots of unity, because zeta is an algebraic integer, so is zeta minus 1. Okay, what equation does it satisfy? Well, if I take y plus 1 to the L, that's zeta to the L, so that's 1. So minus 1. Well, that's equal to 0, but it's also divisible by y plus 1 minus 1. This has got to be equal to 0. Well, what do we get? Y plus 1 to the L minus 1 is y to the L plus L y to the L minus 1 plus Ly. And we divide it by this, which is just y. So you get the equation y to the L minus 1 plus L y to the L minus 2 plus L is equal to 0. So that's the irreducible equation it has to satisfy here. It's irreducible because this is equal to q zeta, but it's also equal to q of y. If you join y, you get the same degree extension. So it satisfies an irreducible polynomial degree L minus 1. In particular, this last coefficient shows that the norm of this element is L, the prime. Its trace is minus L. Okay, well, what does that mean? Well, if you factor the prime L in the ring of integers of this field, so let's call this ring of integers A. In the ring of integers, remember, miraculously turns out to be generated by zeta. And you factor the prime L, well, you have to take a look at the equation satisfied by zeta mod L. And the equation satisfied by zeta mod L becomes a linear equation to the L minus first power, right? And x to the L minus 1 over x minus 1 becomes congruent mod L to x minus 1 to the L minus first power, because x to the L is congruent, right? Okay, so the ideal dividing L in A is an ideal of degree 1 raised to the L minus first power, namely it's ramified and its ramification index is L minus 1. And here, the ideal generated by y is also an ideal of norm L. So there's only one ideal of norm L in A. And that says that P is the principal ideal generated by zeta minus 1. Okay. Well, that says that if you conjugate zeta by any automorphism of this field, you get another ideal of norm L, and it has to be this one. So it says that for all A, or all B, in Z mod L star, zeta to the B minus 1 generates the same ideal as zeta minus 1. Because they both have norm L, and there's a unique ideal of norm L. In particular, their quotient is a unit. That's the big thing. Z of B minus 1 over zeta minus 1 is a unit in A. And this is a remarkable example where you can actually construct units very simply. I mean, the element zeta minus 1 isn't a unit, but if you take the quotient of it by any conjugate of it, you get a unit, because they generate the same ideal. Okay, now let's go over here. We have the same number of conjugates of zeta in the numerator as we have in the denominator. Correct? Therefore, whatever this thing is, it's a unit in the cyclotomic field. Good? But it's fixed by this Galois group. Because if you act by a quadratic residue, you just permute around the terms in the numerator, permute around the terms in the denominator, right? And it's actually inverted by this Galois group, so it lies in this, it's a unit in this field, and it has norm 1. Because if you act by this Galois group, it's taken to its inverse. So call this thing epsilon. So this could be written as 1 over the square root of L, the log of the absolute value of epsilon, where epsilon is a unit in the real quadratic field, Q squared of L. Isn't that nice? Now, we can now do the same thing we did in the imaginary quadratic field. We compare this with the formula that we obtained by the class number formula. If we take K to be Q squared of L, the real quadratic field, and we take the zeta function, we got 2 to the R1, which is 2 squared, 2 pi to the R2, which is 1, divided by the square root of the discriminant, which is L, times H times the log of the fundamental unit, the generator of the unit group, divided by 2, the number of roots of unity. Good? So this is equal to L chi of 1, because we have the factorization of the zeta function, and the residue of the zeta function of the rationals was 1. And we just got a formula for that. That was 1 over the square root of L, the log of the absolute value of this specific unit that we constructed out of these roots of unity. And the conclusion is, since the unit group is cyclic of rank 1, et cetera, et cetera, et cetera, when you work out the details, you find that this epsilon that we constructed was a fundamental unit to the minus 2h power. So we didn't construct the fundamental unit that we would have gotten when we solved Pell's equation using the continued fraction for square root of L, but we got some power of it that was very simply expressed in terms of L roots of unity. These things, by the way, are called circular units, because in the literature, because they come from points on the unit circle, I guess. The zeta's on the unit circle, and you can make combinations of them to lie in subfields like we did here, and they give you units in the subfield. And in fact, it says it says, for example, that this epsilon has infinite order, which isn't completely obvious. I mean, you might have written down some unit which was 1. But since its logarithm was this number, which was non-zero, it wasn't 1. And it gave you a subgroup of finite index in the unit group, and the index gives a formula for the class number. So if you can, and this isn't a terrible way to compute the class number of a, notice that it's always a square. It always has norm 1. This field frequently has units of norm minus 1. Okay, well, you can take this a little bit further. I mean, why just restrict to the case of quadratic fields? We saw, and that was involved in the sort of modern proof that these L functions don't vanish at 1. We saw that if you took the product of all, you took the zeta function, which was the trivial character, times the product of all chi not 1 of Z mod L star, L chi S. That was equal to the zeta function of the field Q zeta. That's bad notation, but never mind. Everyone understands on here. I've used zeta in 2 different ways here. Here's the zeta function, here's the L root of unity. So you got the zeta function of the cyclic comet field of L roots of unity, and maybe I'll put a zeta Ks, where K is Q. So this is just taking the zeta. This says that this is equal to the zeta function of Q times the L function of the quadratic character. But if you take them all, you get the zeta function of the cyclotomic field. So why don't we use all of these formulas? So remember that says that the product, hence the product over chi not equal to 1 of L chi 1 has to be, well, what's the class number formula for the regulator here? It's a totally complex field. There are no real primes. There are L minus 1 over 2 complex places. The discriminant is L to the L minus 2. So you get that. And then you get this HR over how many roots of unity? Well, there are 2 L roots of unity in the L cyclotomic field. And so since we have formulas for this and we know all of this crap, that gives us formulas for H times the regulator. Okay, so what do we conclude from all this? You get 2 very nice conclusions. One is that the units, the circular units, 1 minus zeta b over 1 minus zeta, generate a subgroup of finite index in the unit group in A star. And what you really should do is set it up so they're totally real. So if you take an even better, because the units of infinite order in A star lie in the quadratic subfield fixed by plus or minus 1. So that fixes what's called the real subfield, Q zeta plus zeta inverse. And all the units of infinite order lie in this subfield. And in fact, you can set up these circular units so that they lie in this subfield, and then they generate a subgroup of finite index. And in A star plus, and the index is related to the class number of the real subfield. And what do you get from the imaginary quadratic characters, which is what we did last time? You find that if you take the product, so that's the first thing we get, and the second thing is we get, if you take the product of this for chi odd of the sum b is equal to 1 to L of chi of b times b over L, which is sometimes called the first Bernoulli number of chi, so sometimes they're going to be 1 chi, is related, essentially equal to, but I'm not giving powers of 2 to the odd class number, the class number of the cyclotomic field, divided by the class number of this totally real field. Usually the class number of the totally real field is 1, and all the class group is odd class group, and this gives a way of calculating. So this is something that we really like to generalize to other fields, which we don't have good formulas for their class numbers and good formulas for a good way of generating units. I mean, this is okay. I mean, it doesn't give all the units, but it gives a subgroup, and you know that the index is related to what the class number is. Now, it turns out that, and this is, we'll come back to this, all of these formulas are much nicer when you use the functional equation of the L function and study them not at s equal 1, but at the functional equation part. Remember, the functional equation relates s to 1 minus s. So s equal 1 is taken to s equals 0. So it's actually better, and that was a key observation of Stark, to study L chi s at s equals 0. And we're going to see that the functional equation really distinguishes odd and even characters. So that'll show why this is a somehow simpler formula to study than the one I erased with the logs of the absolute values of the units. So with that prelude, let's at least see what the functional equation looks like and start the proof of it. And then we'll come back to questions of circular units and this class number formula a little bit later. Anyhow, this made a big impression on people in the 19th century that they could use roots of unity to solve Pell's equation. And that's how you could say it, right? I mean, you don't get the fundamental solution of Pell's equation, but you get a solution of Pell's equation. But if you actually want to compute units, the continued fraction for real quadratic fields is infinitely faster. Okay. So what is the functional equation? So Riemann in his paper proves the following, that if you take the zeta function of the rational numbers and you multiply it by the function pi to the minus s over 2 gamma of s over 2, where gamma of s is Euler's function, the integral from 0 to infinity of t to the s e to the minus t dt over t. So that's a function of s that, and this integral makes sense for the real part of s greater than 0, but since it satisfies a functional equation that gamma of s plus 1 is s times gamma of s, you can use this to extend it to all the complex plane with poles, simple poles. We'll do all this at s equals 0, minus 1, minus 2, etc. All the negative integers. So this integral converges and gives a holomorphic function in the right half plane and has a meromorphic continuation. This isn't so different from our Gauss sums, by the way. Remember what the Gauss sum looked like. G of a multiplicative character chi was the sum from a equal 1 to L of chi of a e to the 2 pi I a over L, right? Where, well, this is really over z mod L star, right? So this is a multiplicative character. Chi is a character of z mod L star, values in c star, and this thing, e to the 2 pi I over L, it is a map from z mod L plus to c star. It's a character of the additive group, and we're taking a character of the multiplicative group, multiplying it by a character of the additive group, and then summing over the multiplicative group. Okay. So if I wrote this integral as the integral over r star plus, because that's what the integral from 0 to infinity is, the positive, right? T to the s is pi s of t. It just takes a positive real number and raises it to the s power. So that's a multiplicative character of the positive real numbers, and e to the minus t psi of t, that's an additive character, right? If I add two real numbers, then the values of the exponential multiply, and dt over t is just the measure on the positive real line that I've used to make this sum. So it's a multiplicative character times an additive character summed over the group. All right, anyhow, Riemann said that if you take this function and you call it, let's see what I'm going to call it here, lambda of s. So this is defined for a real part of s greater than, for real part of s greater than 1. It's holomorphic in that region because the gamma function is certainly okay in that region, and so is the zeta function. And he proved that it has a meromorphic continuation to the entire plane. So 1 lambda s has a meromorphic continuation to s in the complex numbers. It has simple poles at s equals 0 and s equal 1. The pole at s equal 1 comes from the pole of the zeta function at s equal 1. The pole at s equals 0, this turns out to be regular, but this has the pole at s equals 0. With residue 1, residues equal to 1. And the second thing he proves is that once you have a meromorphic continuation, you have the functional equation that its value at s is the same as its value at 1 minus s. You can't state the functional equation unless you have the continuation, because if this is only defined for a real part of s greater than 1, then 1 minus s does not have that real part. Okay, so more generally, what we're going to do, so Riemann just did it for the zeta function, but people immediately observed that his methods also worked for the functions of Dirichlet. So we'll do that for Dirichlet characters. So I'll take a character of z mod f star dc star Dirichlet character, and I'm going to assume it's primitive. You can't do the functional equation unless it's primitive. So primitive means that it doesn't factor through any quotient of z mod f star by some divisor of f. For example, it's not trivial. If you did f of prime, all the characters are primitive except the trivial character, right? But you might have a character of z mod h star that factored through z mod 4 star, or a character of z mod l squared that was really just coming from the map to z mod l, and then a character of that. So you want the character to be primitive so that f is really the first integer for which it's defined. And then we divide into two cases. We call lambda chi s. Well, we do exactly the same thing as the zeta function. Pi to the minus s over 2, gamma of s over 2, L chi s. We do that if chi of minus 1 is plus 1, if it's an even character. And if it's an odd character, we do something completely different. We do minus s plus 1 over 2, gamma of s plus 1 over 2, L chi s, if chi of minus 1 is minus 1. We're going to see why all this happens in a minute. All right, and then we're going to prove 1, and this is primitive, and we're going to assume it's non-trivial because the trivial case was handled by Riemann. Okay, so this has holomorphic continuation to all s in C. A priori, it's defined for a real part of s greater than 0, because we saw that this thing was convergent for a real part of s greater than 0, and the gamma function is regular there too. Okay? So it's a holomorphic for all s in C, and it has a functional equation, but it's a little bit more complicated than that. The functional equation looks like this. First of all, lambda chi s. You have a what's called a root number or sign functional equation. You have a conductor, which is f, with a 1/2 minus s power. And then you have the same lambda, but not for chi, but for chi inverse or chi bar, depending on what you want. Times 1 minus s. So in the case of the Riemann zeta function, this stuff is, f is 1, and this number is 1. In general, w chi is given by the formula g chi over the square root of f, the positive square root of f, if chi of minus 1 is plus 1, and it's g chi over I times the positive square root of f, if chi of minus 1 is minus 1, where the Gauss sum of chi is defined as usual, and this has absolute value of the square root of f, so this has absolute value 1. But it needn't be a root unity or anything like that. So this, we're going to attempt to prove this general functional equation. Now notice that this difference in the functional equation makes a huge amount of difference as to what's happening at s equal 1, because we're going to compare the value of this at s equal 1 to how it behaves at s equals 0, right, by this function equation. Let's assume that chi is equal to chi bar is quadratic, so we don't have to worry about that so much. Okay? So this is non-zero at s equal 1. What about at s equals 0? Well, in this case, you see, this has a pole at s equals 0. Right? Gamma of 0 is a pole. And consequently, for this to have the same at s equals 0 as it does at s equal 1, this is regular and non-zero at s equal 1. This is regular and non-zero at s equal 1. So this whole thing is non-zero at s equal 1. So it better be non-zero at s equals 0. If this has a pole, that means this has a 0, a simple 0. So this implies that the order at s equals 0 of L chi s is equal to 0 if chi of minus 1 is minus 1, and 1 if chi of minus 1 is plus 1. Because on the other hand, you see, in this case, this is perfectly okay at s equals 0. You get gamma of a half, which is square root of pi. So in this case, this is non-zero at s equals 0. In this case, this is 0 at s equals 0, and its derivative is non-zero. Okay? So we're going to get a formula when we torture those formulas from s equal 1 of this sort of nature. When we go to 0, it's going to give us a formula, in this case, for the first derivative, and in this case, for the value. And we're going to see that all kinds of nice things cancel out too, like all the pi's and the Gauss sums and all the crap. Okay, so for example, all right, I'll just say that. So that's what we're after. That is the goal. Okay, now the proof, as always followed Riemann, it's gotten more and more sophisticated over the years, is Fourier analysis of the Poisson summation formula. So I'm going to sort of set that up today, or set some of it up today, and we'll get into it next week. I should say that this generalizes, and Hecke eventually proved, let's just do that quickly. Hecke proved the functional equation for zeta of Ks for any number field. Now that's strongly suggested by this because we've seen that we can build the zeta functions of a lot of fields, like quadratic fields, out of products of these L functions. And if each one of them satisfies the functional equation, probably the zeta function does too. And people knew the zeta function of cyclotomic fields and quadratic fields, etc. But Hecke was the first to prove formula for the zeta function of an arbitrary number field. And it looks like this. In this case, you replace this by a function lambda k of s, which is a little bit more complicated. You put this factor in, pi to the minus s over 2, gamma of s over 2, and you put that in for all the real places, R1. And then you put a different factor in for the complex places, 2 pi to the minus s, gamma of s. So you don't take s over 2, but gamma of s. And you put that in for all the complex places. And you call this the function omega k. So that's reflected in the fact and then you prove that this is equal to the absolute value of the discriminant to the 1/2 minus s power omega k upon minus s. So that's going to be the functional equation of the zeta function. And then it gets more complicated when you have characters. But anyhow, that's at least. Now look at what that says at s equals 0. So we saw that at s equal 1, this has a simple pole. At s equal 1, this is regular, and this is regular. So this has a simple pole at s equal 1. So it also has to have a simple pole at s equals 0. Right? Good?
So in the definition of this function, there's no any L function related to the field, it's just a gamma function?
Yes, I mean, we'll see when we put these things together that we get that for real quadratic and imaginary quadratic fields. So for example, for real quadratic fields, you see you get the zeta function, which has a gamma, has this factor in it, and then you get another of these characters, which has this factor, so you get this thing squared, right?
Yeah.
So that's, the R2 becomes squared and the R1 is 0.
Okay.
For an imaginary quadratic field, you get this factor for the zeta function, you get this factor for the quadratic character,
Okay.
but the product of these two turns out to be this, which appears to the first power.
Okay.
Okay? Good. Good question. All right, so since it has a simple pole, so it has simple pole at s equals 0. What does that mean for the zeta function? Well, this thing has a simple pole at s equals 0, right? And likewise, this thing has a simple pole at s equals 0. So this product has a pole of order R1 plus R2, right? this whole thing is supposed to have a pole of order 1. So this has to have a 0 of order R1 plus R2 minus 1. So it says, so the order at S equals 0 of zeta k of S is R1 plus R2 minus 1 by a functional equation. Okay? But that's exactly the rank of the unit group, which we calculated in Dirichlet's theorem. And miraculously, when you take the leading term, we know the residue of this here, right? If we want to work out the leading term at S equals 0, we have to know the leading terms of these at S equals 0 and S equals 1, but that's not too bad. We can do it, okay? And you find that in fact, zeta k of S behaves like S to the R1 plus R2 minus 1 plus O of S to the R1 plus R2, and that the leading term is just minus HR over W. See how it got cleaned up? The 2's went away, the 2 pi's went away, the square root of the discriminant went away, that went away because of this factor in the functional equation, right? So the order is the rank of the unit group, and the leading term is made from a determinant of that size. Right? This is a determinant of a matrix of size R1 plus R2 minus 1. So this is motivating a lot of other conjectures. If you know the conjecture on elliptic curves of Merchant Swinner, it's not a conjecture. The L function is supposed to vanish to the order, the rank of the Mordell-Weil group, and the leading term is supposed to have a regulator, which is the height pairing on the Mordell-Weil group. It's all based on this. And it was Stark who pointed out that the zeta function simplifies at S equals 0, so the L function should also simplify, etc. And so we'll use the functional equation a lot when we look at special values of L functions. And another fact is that also Eagle proved that the values of the zeta function at negative integers are all rational numbers, usually 0 for all n greater than equal to 1. So that generalized Euler's results on the values of the zeta function at negative integers. And it's very interesting to know what these rational numbers are, et cetera, et cetera, et cetera. Okay, so as I say, we're going to have to do some Fourier analysis. And it'll be on the Fourier analysis in this case. To study L chi S, we need Fourier analysis on V mod F, which is, we're going to calculate things like chi hat and G of chi, that sort of thing we've done in the last lecture. And then we're going to also need Fourier analysis on R. And we're going to use the sequence Z to R mod Z a lot. So now when you do Fourier analysis, you need a locally compact abelian group. This is on the additive group of R. This is on the additive group of Z mod F. And like cyclic groups, the real numbers turns out to be its own Fourier dual, canonically its own Fourier dual. So we'll start with that. And so the Fourier transform is going to take a function on the reals and take it to another function on the reals. So self-duality of R. All right, so it says that R is isomorphic to R hat, which are the continuous homomorphisms from R to the circle group. So that if we had a pairing of R cross R to the circle group, a reasonable pairing, that would give us a map from R into Hom R in the circle group. So we define a pairing by the pairing of two real numbers x, y is e to the 2 pi I xy. And one proves that that constructs an isomorphism. If you then, you know, x goes to a map that takes y to e to the 2 pi I xy is an isomorphism from R to its Fourier dual. And okay, now when you do the reason I put the 2 pi I in is that shows that if you take the subgroup Z and you pair it with itself, you get 0. Z is orthogonal to Z under this pairing. It's the orthogonal complement of Z in this pairing. The things that, the characters that give trivial characters of Z are just the integers. And so consequently it gives a duality, so induces a duality of R mod Z. The character group of R mod Z is Z. These are precisely the characters of R that are trivial on the integers. And this is a duality between a discrete group and a compact group. And that tells you in some sense what measures you want to put, because whenever you have a group, a locally compact group that has a discrete subgroup, and the quotient group is compact, what you want to do is you want to put the measure here that gives the measure of volume 1 here and counting measure here. And that's the usual Lebesgue measure such that the integral from 0 to 1 of dx is 1. Right? That gives the measure of volume 1 on this compact group, and it gives, and then you sum it over all integers, and that gives the full measure on the reals. Okay. So what's the Fourier transform look like once we've set up this duality? So if we have a function g on R, Fourier transform, g hat of y is the integral over R, if you can do it, of g of x, the complex conjugate of xy, dx. So this is the character associated. This is really, you know, a function on characters. So this is the character of y applied to x R, right? Because the character of y applied to x is just this pairing of x and y, and we get a function again on R. And you have Fourier inversion, et cetera, et cetera. So g hat of x is g of minus x. So you can recover a function from its Fourier transform. Okay, now we're going to do this in a super general setting to set up what are called theta functions that we're going to use to prove the functional equation. Oh, and let me just at least state Poisson summation. So Poisson summation says, and Poisson summation is a fancy version of Fourier duality when you have a discrete subgroup. It says that if you have a function which is rapidly decaying, so that you can compute the sum over all integers of g of n. So you have to have that sum absolutely convergent, so g has to be very rapidly decaying, that is equal to the sum over n and z of the values of the Fourier transform. That's Poisson summation. So that's a deep identity, and you need a lot of conditions on g for this thing to work. Both g and g hat have to be rapidly decreasing at infinity, etc. An example is the function g, which is used a lot, e to the minus pi x squared. And that miraculously turns out to be its own Fourier transform. That's related to the probability integral, if I did it right, with the pi. And therefore, you get a formula, which is the dumb formula in this case, which says that the sum here is equal to the sum here. But we're going to jazz that formula out quite a lot. Okay, here's how we're gonna jazz it up. Whenever you do Poisson summation, it's only useful if you can compute both sides, if you compute the function and its Fourier transform, otherwise you don't get much of an identity out of it. If you guys want to read a great book on Fourier analysis, at least the greatest book I've ever read, which is one of these books that's set up so you have to do problems to work your way through it. It's this book by Dim and McKean, Fourier Series and Integrals. I think that's awesome. And they do a lot of examples like Gauss sums. I mean, they don't just do Fourier analysis on the real numbers, they do it on a lot of different groups. Okay, so we're gonna fix two real numbers, and we're gonna fix a positive real number. Okay, and we're gonna take a function g of rapid decay. An example will be this function here. Or you might multiply it by a polynomial. Okay, and we're going to define a new function of a real variable, g of w, by taking g, translating x by w, multiplying by t, and then taking the pairing of y with w. So it depends, it's a function of w, but it depends on these fixed x, y, t. You'll see my madness in a second, okay? And this function will also be of rapid decay because this is of absolute value 1. This is just a translation of w, so as w is going to infinity, so is this. And this is just a scaling. So again, if this w is going to infinity, so is this. So this is rapidly decaying. This is of absolute value 1. So this is rapidly decaying, and I can calculate its Fourier transform. Okay. Anyhow, I will do that for you. But I can also define its theta function, and I'll call that theta t xy. So again, it depends on these two real numbers and a positive real number. They occupy slightly different roles. And that's what I get by summing g over the integers. And I'm going to prove a functional equation for this theta function, which now depends on t, x, and y. Now these somehow become the variables. I'm going to prove something about this by calculating the Fourier transform of this, and you know, I mean, that's going to be equal to the sum of whatever its Fourier transform is over the integers, that by Poisson summation. But what I have to do is tell you what the heck the Fourier transform is in terms of the Fourier transform of g and this x, y, and t. Okay. So the formula I'm going to prove for the Fourier transform is that, looks a little weird, but here it is. I'll do that next time. Is that g hat of u, and you can try this yourself, is xy bar over t, the inner product of u with x, g hat of u minus y over t. So notice what's happened. First I've gone to the Fourier transform of g. Then instead of translating by x, I now translate by y. Instead of taking scale inner product with y, I'm now taking the inner product with x. Right? Instead of scaling by t, I'm scaling by 1 over t. So somehow or another, this is related to the theta function of t inverse yx. Right? So this is going to be equal to, and we're going to do this then, so we have to prove. If we are able to prove this, then this is going to be equal to xy bar over t. So that's some complex number of absolute value 1 divided by a positive real number times theta of well, let's call this depends on g, of course, theta g of txy of, yeah, t inverse minus y x. So I've inverted t here. I hope I did that right. Yeah, I pulled this factor I just pulled out. The y is replaced by x, and the x is replaced by minus y. And that's going to be my big functional equation. Now look what happens if I take, for example, the function g is equal to e to the minus pi x squared, where I know what its Fourier transform is. What is theta g txy? Well, I claim it's the sum over n and z, e to the minus pi. Now I have to take x and translate, whoops, I better call this g is, u or something, I don't know. So I have to take that variable and translate it by x plus n squared, t squared, plus 2 pi I n y. So I'm summing a quadratic thing in, and if I even simplified it more, and I said x equal y equals 0, so I got rid of this term, it would be the sum over n and z of e to the minus pi n squared t squared, which is the usual theta function. And if you use the fact that g is equal to g hat, this gives an identity for that, right? Because even though x and y are 0, I replace t by t inverse. And it says that the value of this here is another series. And this is the kind of generality we're going to need for the functional equation of a theta function. This is enough, this identity, by the way, for this particular g is enough to do the Riemann zeta function if you take x and y as 0. But we're going to need to take x things like, a over f and things like that to do Dirichlet-Gauss functions. So see if you can do this computation yourself, and we'll start off with it next time. Take a function, define a new function this way, see if you can calculate its Fourier transform in terms of the Fourier transform of g. And we'll start with that next week and then go on and do the functional equations. Good? Okay. And then, this is sort of where people were at the beginning of the 20th century. And then Hecke, I should at least tell you the historical development. So this is all Fourier analysis on R, and on R mod Z, and on Z mod F. So what Hecke did was to prove the functional equation zeta function of a number field, he went to n-dimensional space where he did Fourier analysis on R tensor K, which is R to the R1 plus 2R2. That's certainly a nice additive group. And inside of that, he had the discrete subgroup, which was the ring of integers. And so that played the role of Z inside of this real vector space. And instead of this Z mod F, he had A modulo various ideals. So he first did Fourier analysis on the reals with this lattice, and then he did Fourier analysis on these finite abelian groups. And then Tate in his thesis put all this together and said, instead of doing it in two pieces, which became increasingly complicated. I mean, this is already fairly complicated to just do Dirichlet-Gauss functions, but Hecke-Gauss functions are incredibly complicated. Instead of doing that, he replaced this whole thing by using this notion of adels that Chevalley had introduced, and he studied K as a discrete subgroup of the adels of K with compact quotient, and did the Fourier analysis on the abstract adels, but this is a discrete subgroup with compact quotient, and that handled both of these two things at once. So I'll at least preview that so that if any of you want to do as a project case thesis, you'll be able to see how it relates to all this classical work. And of course, Kate needed the Poisson summation formula, which in this case is a sum over elements of the discrete subgroup K. Okay? There is a number theory seminar today that was posted a little bit late by a local speaker, right? And there'll be a pre-talk of that
1 o'clock.
at 1 o'clock.
1 o'clock.
1 o'clock, this room?
1:20.
1:20, this room, 2 o'clock, this room for the real thing. Okay.